What we're going to take a look at in this lecture is how to describe a situation in which a person can move from one state to another using matrices. We call these transition matrices, and ultimately what we're going to be able to do with our transition matrices is compute the probability of certain events happening after a couple of moves or 10 moves, or ultimately what the long-term prediction would be if we imagine that we allow a person to move from state to state forever. Okay, let's get into it. So suppose there are three bins, A, B, and C. So I'm in a store and I have three bins, A, B, and C, and every day I take some of the objects from one and move them to another. Suppose the probability of moving from A to B is 15% and from A to C is 22%. Implicit in that is the idea that staying in bin A happens at a probability of 63%. The probability of moving from B to A is 10%, from B to C is 70%, so there's a 20% chance of staying in B. And then the probability of moving from C to A is 8%, and from C to B is 60%. So first what we're going to do is take these three lengthy sentences and basically boil them down into an efficient diagram. That's already useful. Then we'll take that diagram and convert it into a matrix. That will be our transition matrix. Okay, so let's start with just that diagramming action. So what we have are three bins, A, B, and C. So I'll just do A, B, and C. And then we'll say the likelihood of moving from A to B can be represented with an arrow that takes us from A to B, and we'll label that arrow 0.15. That's the probability, 15%. From A to C was 22%, so I'll do an arrow from A to C and label that 0.22. And then to represent the action of just staying in bin A, I'll do like a looped arrow back from A to A and we'll label that 0.63. Okay, from B to A is 10%, so we'll do a little arrow like this with a 0.1. From B to C is 70%, so we'll do like that. And then from B back to itself is 20%, so just a little arrow to indicate that you can stay in bin B. And then from C to A is 8%, so 0.08. From C to B is 60%, so 0.6, and then C back to itself is 32%. Okay, so I said the diagram was going to be a lot better than the three sentences, but maybe it's not because there's a lot happening. But this is the idea with these transition activities that we're going to be looking at, is often the first step is to try to visualize it with some sort of diagram. So we see that there are three boxes that you can be in. And also we see the direction of travel between them. It's not going to always be the case that you can get from one box to another. In this case it is. Okay, what I'm going to do is copy this diagram over onto the next slide. And then once we have that, we'll set up our transition matrix. That will actually be the most efficient way to represent this information. Here's our diagram. And what we're going to do is make a matrix now. It's always going to be a square matrix, and the dimensions of the matrix is the number of bins. So in this case, it's going to be a 3 by 3 matrix. The entries in the matrix are going to be the probabilities that you move from one to another. How we're going to organize this is we'll think of the columns as being from. So I'll label this like from at the top, and then from A, from B, from C. Those will be the first, second, and third columns respectively. And then the rows are where you end up. So we could go from A to A, from A to B, from A to C, etc. For me, it's easiest to fill these out column-wise. So what I'm going to do is go down each column because I look at this diagram and it's easier for me to track where you're going from. So the first column is going to contain entries that represent all of the ways that you can travel from A. So you could go from A back to A, and that happens with a probability of 0.63. You could go from A to B, that's 0.15. From A to C, that's 0.22, just reading these off the diagram. And then in the second column, it's how to go from B to somewhere else or back to B. From B to A is 0.1, so that's that entry. From B back to itself is 0.2. and from B to C is 0.7. I hesitated there because I was trying to find it on the diagram, but actually you have to go somewhere. So one thing you can recognize is that the columns here are going to sum to 1. We'll come back to that in a minute, so let me go ahead and fill out the column for C. We could go from C to A. That happens at probability 0.08 or 8%. From C to B is 0.6. And from C back to itself is 0.32. Okay, so I'll go ahead and make a note here that the columns all sum to 1. We're going to visit this terminology later, but I'll go ahead and make a note that such a matrix where the columns all sum to 1 is called stochastic. So let's look at these questions here. We're going to go ahead and answer them. So I'll just state what the answer is going to be in terms of this matrix, and then we'll dig into why it works. So what is the probability that an item which began in bin A will be in bin C after 1 day? Well, that's easy. You just look down here at this entry in the first column. The probability that in 1 day, if we always move just once per day, you go from A to C is 22%. Now take my word for it for now because we'll get into it in a minute. What's the probability that you would start in bin A and find yourself in bin C 2 days later? Well, for that, what we're going to do is take the matrix A and square it. Matrix multiplication is a pain to do by hand, so let me open up MATLAB Online. Okay, here we are in MATLAB Online. I'm going to click New Script, and I'm going to put the matrix in a script. So we'll call it matrix A. Actually, let me call it M for matrix. First row is 0.63, 0.1, 0.08. Notice those don't sum to 1. The columns sum to 1. So the second row is 0.15, 0.2, 0.6. And then the third row is 0.22, 0.7, 0.32. You can always check if you've done this correctly. If you do sum M, the way MATLAB does that command is it does the column sums. So sum is one of many commands in the MATLAB toolbox that goes column-wise. Similarly, just to mention it, if you do something like mean of M, that's going to be each column's average, which of course is a third, because each column sums to 1 and there are 3 entries. Okay, so let's just go back to sum of M. Okay, so that means that we set our matrix up correctly. Now if I do M squared, just plain old exponentiation, not array exponentiation, just regular caret, and you run it, you get this matrix. Let me copy this matrix into the slide and then we'll return to that. Okay, so here's that matrix. I just figured out that if I copy in my computer and then paste on my iPad, it will actually paste the text. So I just copy that directly from MATLAB. The columns and rows here still have the same meaning. So the first column is from A and the third row is to C. So this entry here tells us that there's a 31.4% chance that after 2 days, you would find that you had started in A and arrived in bin C. There's a 42.95% chance that you would still be in A. That doesn't mean that you never left A, but rather you started in A, you did your day 1 action, and after day 2, you're back in A. And there's a 25.65% chance that after 2 days, you would have moved from A to B. Let me go back to that matrix in MATLAB now. One thing to notice is that the column sums are still all 1 because you have to be somewhere. So there's like a 100% chance that you're somewhere. And now if I want to find out the probability that I would start in A and find myself in C 3 days later, you just do M cubed. And you can see that that would happen with probability 37.45%. What we'll do now is justify why this exponentiation process is the correct notion. And then we'll talk about how to make a long-term prediction. So what I'm going to do is rewrite the transition matrix. This time, instead of putting in explicit probabilities, I'm going to indicate the type of transition that we're making. So in particular, the first column is going from A to A, from A to B, and then from A to C. That's what those entries represent. The second column is from B back to A, or from B to B itself, and then from B to C. And then the third column was C to A, C to B, and C back to C. Let's see what the entries look like if we take this matrix and multiply it by itself. So in particular, m squared is the product of that matrix with itself. Okay, I'm going to do this matrix product by hand now. I might not fill out the whole thing because it's going to be a lot to write down, but we'll certainly do the first column at least so that we can see how you could travel from A with 2 steps. Okay, the first entry in the column of this product is going to come from taking the product of this row with this column. So that's going to be A to A to A. So that's the product of the first entries. And then from B to A to B. So we add to it B to A to B. And then add to that C to A to C. I wrote these terms in the order in which I encountered these entries as I did this product, but multiplication of numbers is commutative. So I'm going to take that middle entry and just switch the order. Instead of writing B to A to B, let me just write A to B, B to A. It's the same product. And then similarly for that third term, instead of doing the probability C to A times the probability A to C, I'm just going to switch the order of those two terms. So we'll do A to C times C to A. It's the same product. Okay, and now for the second entry in this column, it's going to be from this row, the second row, times that first column. Following the adjustments I just made on the first row, I'm going to write the terms from the right first, and then the terms from the left. So it's a bit reverse order from how we normally write down multiplication. So my first term is going to be A to A times A to B. And then my second entry is A to B, B to B. So A to B, B to B. And then A to C, C to B. And then lastly, for the third entry in that first column, it's going to come from the third row times the first column, and writing those products in the reverse order, reverse of what feels like the most natural way to write down the multiplication of two numbers, we're going to get A to C, plus, and then A to B, B to C, plus A to C, C to C. That's the entire first column of this product here of M with itself. So you can see I'm not going to do the whole thing, but you can actually anticipate what they would look like if you've understood the pattern that we're looking at in that first column. So what is this first entry? This represents the sum of probabilities of going from A to A back to itself. So this is like stay in A. This is on day 1, go from A to B, and then on day 2, go from B back to A. And this is on day 1, go from A to C, and then from C back to A. These are all of the ways with 2 steps to start in A and finish in A. So you could either stay in A, you could visit B and then come back to A, or you could visit C and go back to A. The second entry is you could stay in A and then go to B, you could go directly to B and then stay in B, or you could visit C and then go to B. Those are all of the ways to start in A and end in B after 2 days. And similarly, the third entry in this first column is stay in A, then go to C, first visit B, then go to C, or go to C and then stay there. You could check that this would happen for the other 6 entries, or you could do a couple of them and then anticipate what, say, this entry, the third entry in the second row would have to be. That would be all of the ways to start in C and end in B after 2 days. So stepping back and looking at this matrix product, say I take this third entry in the first column. This sum gives us the probability of starting in A and finishing in C in 2 days' time. You can think about what it would look like if we did m cubed. What would you expect it to look like? And then you could actually do the product to verify that the way the probabilities are added together matches your expectation. Or you could kind of think about it as like m squared times m. What would happen if we took this matrix and multiplied it again by m? How would that represent shuffling these items around between these three bins? Okay, let's make a long-term prediction. What we're looking at right now is where you would land after 3 days. So for example, there's a 16.13% chance that you would start in C and arrive in A after 3 days. What happens after a year? Notice here the columns are all the same. And now let me just do m to the 1000 power. That's obviously not something you can do by hand, but MATLAB can do this pretty easily. MATLAB stands for Matrix Laboratory, so it's built for matrix operations. And you can see that, again, the entries are all the same. If I throw on another 0 here and do m to the 10,000, you don't want to go overboard and do like 10 billion, but let's start here with m to the 10,000, and you can see that the entries didn't change. Just for fun, let me do 100,000. I run it, and again, it doesn't change. So I'm going to copy this matrix over back into the slides, and we'll talk about what's happening. What we just observed in MATLAB was that as we took higher and higher powers, our matrix stabilized on this one particular square matrix. That happens a lot when you're looking at these kinds of processes. What this is telling us is that if you start in A, where you land is represented by this first column. So an item which starts in A will long-term be predicted to be in A at a probability of about 19%. An item which began in A will arrive in B long-term, that's the long-term prediction, with a probability of about 37%. Here I'm just rounding. And lastly, you would end in C at a probability of about 44%. But these probabilities are actually the same if you started instead in bin B or bin C. It doesn't actually matter where you began. So to answer the question up here, what's the probability that an item will end up at B? It's 36.62%. And the key observation that we have here is that your starting point doesn't matter. That actually shouldn't be surprising if we're talking about a long-term end behavior as n goes to infinity. That's because if you start in A and after 1 day you arrive in B, but then the days grow infinite, it's not really that different than just starting in B, right? Going from A to B on day 2 shouldn't lead to a dramatically different trajectory than starting in bin B on day 1. At this point, I think we've seen the most interesting result about our transition matrix, which is that a high power of it tells us where we're going to end up. But let's take a quick look at a couple different questions that you could answer with the transition matrix. So in particular, instead of just focusing on having one item move around, suppose we actually have several items and we know how they're distributed. So suppose on day 1, I start with 100 items in bin A, 40 items in bin B, and 200 items in bin C. How many items would be in each of the bins after 1 day, after 2 days, and long term? Let me copy down the matrix M that we've written before. If I take this matrix and multiply it by the vector containing the current distribution of these items, so that would be like 100, 40, and 200, I claim the result of this product is going to give us how these items should be displaced after one day. So here's what we would expect. The first entry in this product is going to be 0.63 times 100. Let me just write 63 plus 4 plus 8% of 200, which is 16. Okay, what do each of these numbers represent? Well, if we have 100 items in bin A, then according to our probability, we expect 63% of them to stay in bin A. So that's the 63 here. If we have 40 items to start with in bin B, we predict that 10% of them will move into bin A. So that's the 4 here. So this is like A to A, this is B to A, and this is C to A. If we go back into MATLAB to finish this product, what I can do is create a vector. Let's call it P for placement. And this is going to be 100, 40, 200. And then we can do M times P. And we get these terms. The second entry, 143, comes from taking 15% of 100 items. That's moving from A to B. 20% of 40 items, that's staying in B. And then 60% of 200 items, that's moving from C to B. And then similarly, 114 is all of the ways that after one day, we would arrive in C. Now what we could say is, well, what would happen after another day? That would be like taking this product we just did, M star P, that's the vector that we're looking at in the command window, and then doing M again. Or in other words, it's like M squared times P. No array exponentiation or array product here, it's just plain old exponentiation and regular product. Numerically, we end up with decimals. If we're talking about items, it doesn't make sense to say 75.7 of an item, but of course, MATLAB doesn't know, and these are just numbers. So here's what we would expect for our placement after 2 days. And then you could do 3 days, 4 days. See that things aren't moving around that much anymore. And then we could do, 10,000 days, 100,000 days. Again, don't go too overboard with doing a matrix exponentiation there. You should be able to see the result with a smaller power than 100,000. This tells us that long term, we expect about 66 items to end up in bin A, about 124 items to end up in bin B, and 150 items to end up in bin C. Okay, so let me go back to our slide. So if n is the number of days, we want to do m to the n times this vector telling us where all of the items started. So this gives us how we should predict the arrangement to look like on the nth day. Let's change it up a little bit. Instead of having 140 and 200 items in the 3 bins, let's put all 340 items in bin A. So how many items are in bin B after 2 days? What we're going to do is take this matrix, square it, and then multiply it by some vector telling us that all of the items, all 340, started in bin A. Let's just do this in MATLAB now, so I'm going to go back to MATLAB Online. Same matrix as before, but this time we have 340, 0, and 0. Okay, let's just start with m times p. After 1 day, we predict that A still has the largest number of items because so many began in A, and of those, we expect 63% to stay in A. Some items have moved into B and C, so after 2 days, we would expect to have about 87 items in bin B. After 3 days, now A doesn't even have the highest number. 4 days, kind of see that the initial condition doesn't look like it matters as much anymore, so let's just do 10,000. And if you recognize those numbers, it's the same as what we got with the previous problem. So whether we begin with 100, 40, and 200 in the 3 bins, or we put all 340 items in the same bin, after 10,000 days, we expect them to have settled into this configuration. We realize that the first few days don't matter because things are going to get shuffled around, and when you're looking at a long-term behavior, you're interested in the ending more than the beginning. So it doesn't matter if the items were in A to start with, this is how they finish up. We understand that out loud, but let's look at mathematically why that argument makes sense. So why didn't the initial arrangement really matter? Where do you see it in the numbers? Well, recall that without even having a placement vector, we knew what m to a really large power would have to look like. So let's just say that we've placed items as, how about A, B, and C? We don't really care what those numbers are. Could be 340, 0, 0, could be anything. If I do this product now, using that expression for m to the n at the top, it's going to be 0.1941 times A plus 0.1941 times B plus 0.1941 times C. And then same story in the second row. Let me just go ahead and factor out the 0.3662 that we're going to see everywhere and write that as that number times A plus B plus C. And then this number, 0.4397, would also be multiplied to each of A, B, and C, and then they would be added together. Which means that we can actually factor that expression A plus B plus C out in front. And we're just left with that first column, really, 1941. Any of the columns, actually, because they're all the same. So 0.3662 and 0.4397. So when we looked at the configurations, A, B, C was, I believe, 100, 40, and 200 versus A, B, C was 340, 0, 0. Regardless of what those coordinates are, the sum, A plus B plus C, is 340 for both of them. In this product, only the sum mattered, not what the individual terms A, B, and C actually were. Notice this also gives us a shortcut for how to do this kind of problem. If we have our m to a large power matrix, this kind of stabilized matrix where the entries aren't changing as n goes to infinity, if I want to know how my items should be placed after enough time has gone by, all I have to do is take the column, this repeated column that we're looking at here, and multiply it by the total number of items that I'm working with. I don't have to do this kind of individual matrix multiplication here because we don't care about A, B, and C as a vector, really. We just care about the sum. Let me summarize what we've been looking at, and then I'm going to go into a proof of why this works when m is 2 by 2. So when we have like a two-state condition. That proof is going to use eigenvalues and eigenvectors. So if you're familiar with that and you enjoy that material from linear algebra, great. If you're unfamiliar with eigenvalues and eigenvectors or you'd rather skip it, that's fine too. Because from, say, bin A, you have to go somewhere, each of the columns sum to 1. A matrix of non-negative entries whose columns sum to 1 is what we call a stochastic matrix. It turns out that there's always a vector, which I'm going to call u, whose individual entries sum to 1, and which is fixed by m. So in other words, m times u returns back u. What we observed for the matrix that we were looking at the top was that if I took m and raised it to a really large power, I ended up with a column getting repeated 3 times. This column is actually that vector u. We didn't actually talk about the fact that m fixes u. So if you take m and multiply it by this column here, you're going to return back that column. But that's what happens. So what we saw was that as n goes to infinity, m to the n turned into this repeated column. Now that's not always going to happen 100% of the time, but it usually does. There are certain hypotheses where it's guaranteed to happen. For example, If all of the entries in the matrix are positive, like what we had at the top of the page, it will happen. But it also happens even if that's not necessarily the case. So basically, it's always worth checking. And when you check that, if you have a stochastic matrix, perhaps with zeros in here or something like that, but when you exponentiate it, it settles into one column repeated, then what that column U gives you is the long-term probability of arriving in that state. So the first entry of U is the long-term probability of being in state 1. The second entry of U is the long-term probability of being in state 2, etc. Let me just pull up MATLAB now and show you how m to the u equals u, because that didn't really come up in our calculations. Okay, what I'm going to do is m to the 10,000, and then I'm going to let u be, how about the answer? That just refers to this calculation that we just did. All rows first column. Okay, so there's u. Now if I just go back to plain old m, so I do m times u, it returns back u. You can put them side by side. You could do m times u and then u just to compare. And you see that u is being fixed by the action of m. We just made several claims about how stochastic matrices work long term. I'm not going to do the general proof. There are theorems for that. But I will show you why it works when you only have two bends. We haven't used the word Markov yet, but we will in the next lecture. This is what you could call a two-state Markov chain. So suppose we have two bends A and B, and I'm just going to pass immediately to the matrix. No point really diagramming with two bends. So suppose the probability of moving from A back to itself is 1 minus P, whereas the probability of moving from A to B is P. If you're wondering why I wrote 1 minus P and P like that instead of vice versa, it's just going to make the calculation a little bit nicer. The idea here is P is some probability. It's actually the probability of going from A to B. If that's 0.3, 1 minus P is 0.7. That gives us our stochastic column summing to 1. Okay, going from B to A, we'll write that as probability Q. That's between 0 and 1. So going from B back to itself is 1 minus Q. Okay, so there's our matrix, and I'll go ahead and label. This was from A or to B, and the second column was all the ways to leave B. And here, P and Q are strictly between 1 and 0. I'm saying strictly because we're assuming that we're in the case where none of the entries in M are 0. They're all positive. Okay, the rest of this is going to assume familiarity with linear algebra, so I'm going to do some steps here that if you haven't done eigenvalue and eigenvector computations recently might seem unmotivated, but I'm assuming that if you're watching this, it's because you do have a background in that. So what I'm actually going to do is pass to M transpose because it's going to give me a result a little bit faster than if I stay with M. So what is M transpose? That's just flipping rows and columns. So that's going to be 1 minus PQ and then P 1 minus Q. So here the row sums are 1. I claimed that 1 is an eigenvalue of M transpose, and it's easier to see with this transpose matrix because I can actually invent an eigenvector out of thin air. So since, let's write 1 minus PQ, P 1 minus Q, times the vector 1, 1, returns you back 1 minus P plus P and Q plus 1 minus Q. Notice that returns you back 1, 1. And in fact, let me write that as the number 1 times the vector 1, 1. That is exactly what it means to say that 1 is an eigenvalue of M transpose with eigenvector 1, 1. I don't actually care about the eigenvector here, I just care about that eigenvalue. Now notice the magic that happened here when we did this matrix product. That's always going to happen with the transpose of a stochastic matrix and the vector of all ones. So if you're like, how does she know to do that? It's because this is just a common step that you see when you start learning about these stochastic matrices. So transpose it, multiply it by this vector, and boom, you've got an eigenvalue eigenvector situation. With a 2 by 2 matrix, it's really quick to get the other eigenvalue. The trace of any matrix is the sum of its eigenvalues. So since the trace of M transpose is 2 minus P minus Q, that's the sum of the diagonal entries. And then that's also going to be lambda 1 plus lambda 2. This is just a fact about matrices. If you have a square matrix and you compute its trace, that's the sum of the associated eigenvalues. This tells us that we can solve for lambda 2. We know that lambda 1 is 1, so if I just subtract that over to the other side, I get 1 minus P minus Q. You might already know this about eigenvalues, but if you don't, let me just remind you. For any n by n matrix, in this case we're just looking at a 2 by 2 matrix, the eigenvalues satisfy that 0 equals the determinant of that matrix. Let me call this matrix A just to distinguish between speaking generally versus speaking about our particular matrix M here. So determinant of A minus lambda times the n by n identity matrix. If you do eigenvalue calculations all the time, you know what this is, even if you don't recognize the terminology. That's taking A, subtracting lambda off the diagonal, computing the determinant. That gives you the characteristic polynomial, and that's the traditional way to find eigenvalues. Up here, we had kind of a shortcut. But the determinant of any matrix is the same as the determinant of its transpose. It's just algebra. So I could do determinant of A minus lambda in, that quantity transposed, but then that's really just like taking A transpose and subtracting off lambda in transpose, but the identity matrix is symmetric. So that's really determinant of A transpose minus lambda in, and that's exactly the characteristic polynomial that you would get if you were trying to find the eigenvalues of A transpose. So the moral of the story here is that A and A transpose have the same eigenvalues. Passing back to the matrix that we started with in the top left corner. Now we know that the eigenvalues of M are also 1 and 1 minus P minus Q. Now it is not true that A and A transpose or M and M transpose would have the same eigenvectors. So I'd now like to come up with the eigenvectors of M, but I'm going to have to do this manually. Let's go over to the next slide. Okay, so to finish the story, let me find the eigenvector associated with our first eigenvalue of 1. To do that, we're going to take M and subtract 1 off the main diagonal. In other words, if I do M minus 1 times the 2 by 2 identity matrix, we get negative P, Q, P, negative Q, and now you can see why I did that sort of weird 1 minus P in the top left corner, just so that the 1 would cancel out. We're trying to find an eigenvector, so we do a little row reduction here, and we end up with, how about P and negative Q, 0, 0. So I'm doing like some Gaussian elimination type maneuver there. Now what we want are coordinates V1, V2, so that if I did this product, I would end up with 0, 0. In other words, we kind of want that first row times that column to cancel out. That tells us that our eigenvector V is going to be, let's see if I do Q and P, we'll have PQ minus QP, so QP will be an eigenvector. Let's do the second eigenvector now. So for lambda 2 equals 1 minus P minus Q, our matrix would be 1 minus P minus 1 plus P plus Q. Overall, that's going to give us Q. And then Q, P, and then same story. 1 minus Q minus 1 plus P plus Q leaves us just with P. This actually simplifies really nicely into just 1, 1, 0, 0. So that tells us that this eigenvector is just 1, negative 1. So M is what we call a diagonalizable matrix, and in particular, we can decompose M now as the product of a matrix whose columns are these eigenvectors, Q, P, 1, negative 1, times a matrix which is diagonal containing the associated eigenvalues. So 1 and 1 minus p minus q, 0, 0. Let me give myself a little bit more room there. 1 minus p minus q, and then 0 and 0 on the off-diagonal entries. And then times the first matrix inverted. Okay, let me write this out again. I'll leave the first two matrices alone. So Q, P, 1, negative 1, and then 1, 0, 0, 1 minus P minus Q. Then I will not necessarily use this matrix in the next line, but we'll need it eventually. So let me invert that third matrix. For 2 by 2 matrix, it's always easy. You switch the entries on the main diagonal. So that's going to be negative 1 and Q. And then you negate the other entries, so negative 1, negative p, and then you multiply it by 1 over the determinant, which is negative q minus p. Okay, we'll probably save that for later. Let me now look at what it would look like to take m and raise it to a really large power. So in particular, this matrix is not going to matter in the next computation, so let me call that S, so that this is S inverse. The middle matrix is more interesting to us, but let me give it a shorthand too, so let's call it D for diagonal. Okay, the next step is, what is m to the n? Well, you would just do SDS inverse times itself n times, so let's do that. M to the n would be SDS inverse, that's one copy of m, times SDS inverse, that's another copy of m, times, and you would multiply that out till you did n of them, so that's the nth copy. But what you see is that all these middle pairings of S inverse and S are going to cancel and leave you with S d to the n, because all of the interior S's and S inverses cancel out, so you end up with d times itself n times S inverse. And now I will stick with S, but for d, let me write d to the n. Because d is diagonal, it's actually an easy matrix exponentiation to do by hand. It's going to be 1 to the n, 0, 0, 1 minus p minus q to the n, and then times S inverse. 1 to the n is just 1. Because p and q are probabilities strictly between 0 and 1, 1 minus p minus q is smaller than 1, but it can't go all the way down to negative 1, because p and q are not quite big enough. So if p is 0.8 and q is 0.8, this is 1 minus 1.6, that would be like negative 0.4. So you can't go all the way down to negative 1. So this is like b to the n, where b is strictly between negative 1 and 1. That means as n goes to infinity, b to the n goes to 0. So what we can say is d to the n is going to go to a very simple matrix. The first entry is 1, 0, 0, and then something which is basically 0. For large powers of n, that's going to be negligibly small. So m to the n is going to go to, now I'll bring the actual expressions for S and S inverse back into it. Let me write that determinant out front. I'm also going to kind of like go through and flip all these positive, 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 negative, positive, positive. Okay, just I think I'm less likely to make a mistake with positive terms. So let me write 1 over, how about p plus q? And then we'll have q, p, 1, negative 1, times 1, 0, 0, 0, times 1, 1, p, negative q. There's a fast way to do this product because that middle matrix is just zeros and ones, but we can do this out in full detail. So if I do the first two matrices together, I'm going to get q plus 0, and then 0, and then p and 0, so p, and then 0, like that, and then times the matrix I didn't use, 1, 1, p, negative q. And now I'm going to get q and 0. I'll go ahead and divide that by p plus q. So it's going to be q over p plus q. and then p and 0, so p over p plus q. And then for the second column, it's q and 0, so q over p plus q, and then p and 0. So once again, p over p plus q. Notice that the columns are the same, so that's like seeing that repeated column. These columns are the same. It's what we're going to claim as the vector u. And actually, if you're with me this far, then it means you like eigenvalues and eigenvectors. So if I come back here, u is an eigenvector with eigenvalue 1. That's exactly what saying u is fixed by m is. U is an eigenvector with associated eigenvalue 1. So if I come back here, notice that if I take the sum of the entries in the eigenvector v up here in the top right corner, it's p plus q. So we could say u is take v and divide it by its own sum, q over p plus q, p over p plus q. This is also an eigenvector with eigenvalue 1. I've just taken the eigenvector v and scaled it by 1 over p plus q. So this also works for that eigenvalue, and we now see that it's that repeated column. So regardless of the values of p and q, as long as they're probabilities between 0 and 1, this would have to happen for any 2 by 2 matrix. A little harder to do this for higher dimensional matrices, but I wanted to show you, if you have a background with linear algebra, how it does work when you have 2 states that you're moving between, because I think it is neat to see this kind of happen at the end here. This also gives you the form of the vector u for any 2-state computation. So it must be that probability q divided by the sum p and q, and then the probability p divided by that sum. In the next lecture, we'll look at some more examples of transition matrices and we'll do some problems. They won't always be 2-state problems, nor will they necessarily have this property that the matrix entries are all positive. Some of them might be 0, but we'll see that it's not going to matter. So we're going to be able to use the same techniques.